So let's begin our study of magnetic field with its effect on charged objects, and then later we investigate the origin of magnetic field. So recall that we represent electric field with the vector E, and for magnetic field, in this class, we represent it with the vector B. So you might be wondering why not M? Vector M? Well, vector M is already used for magnetization vector. Next, why not vector A? Meaning to say we start with the first letter of the alphabet. Well, vector A is used for vector potential. We use vector B because this is the representation used by James Clerk Maxwell. When he published his papers, well, the whole world also used his notation, and that's vector B for magnetic field. Imagine we have a uniform magnetic field going to the right, and if I place a stationary positive charge in this region, experiments show that this charge is not affected by the magnetic field. In other words, this charge experiences zero magnetic force due to this magnetic field. Now, when this charge has an initial velocity v that is parallel to the magnetic field, it also turns out that based on experiments, this moving charge is not affected by the magnetic field. In other words, it still experiences zero magnetic force. Also, when this charge or positive charge has a velocity that is anti-parallel with respect to the magnetic field, it also experiences zero magnetic force. However, when this charge moves with a velocity v in such a way, this velocity has a component that is perpendicular with respect to magnetic field, then this charge experiences a magnetic force. If I try to draw it in a three-dimensional manner, imagine this is the x-axis. This is the y-axis. And this is the z-axis. If the magnetic field is along the y-axis and the charge has a velocity that is along the xy plane, then this charge experiences a magnetic force that is along the z-axis. Let's assume there's another charge here and its velocity is perpendicular to the magnetic field. It turns out that the magnetic force experienced by this charge is maximum when its velocity is perpendicular with the magnetic field. So based on experiments, the magnetic force experienced by a charge Q is directly proportional to the magnitude of the charge. Also, the magnetic force is also directly proportional to the strength of the magnetic field. And finally, the faster the charge, meaning to say, the greater the magnitude of the velocity of the charge with respect to the magnetic field, the greater the magnetic force it experiences. So its magnetic force is also directly proportional to the velocity of the charge. However, based on the previous discussion, this is not simply directly proportional. It also turns out that the strength of the magnetic force is also directly proportional to sine theta, and theta here is the angle between the velocity vector of the charge and the magnetic field vectors. Now, if I write the magnetic force magnitude in terms of these quantities, notice that this term here is the magnitude given by a cross product. So essentially, in vector form, magnetic force on a charge is equal to Q times V cross B. And since charge here is a scalar quantity, I could actually put it inside. So this is just the same. Let me emphasize that because of this cross product, the direction of magnetic force is always perpendicular with respect to the plane created by velocity vector and the magnetic field vectors. The SI unit of magnetic field is Tesla, abbreviated as capital T. And we also have another unit for magnetic field, which is Gauss, represented by capital G. And 1 Gauss is equal to 10 to the negative 4 Tesla. This unit is helpful when we're dealing with magnetic field produced by the planet Earth, because usually the magnetic field on the surface of the Earth is 0.25 Gauss to zero point 0.6 Gauss, so it's actually near 1 Gauss. And this is the magnetic field that is actually detected by a regular compass. Let's try to draw the magnetic field lines of common sources of magnetic field. First, the most common source of magnetic field is a permanent magnet. Permanent magnet actually contains a lot of magnetic domains or a bunch of molecules that produce current loops. Now, when we draw the electric field line of a permanent magnet, it actually does not originate from a particular point in space, but rather it is a continuous field of line. For example, we can imagine it starting from the North Pole, going out of the magnet, and then continues to terminate at South Pole, but actually it reconnects itself inside the permanent magnet. So its direction is somewhat emanating from the North Pole and then terminating to the South Pole. So it looks like this, but I won't show all the magnetic field lines inside the permanent magnet. I'll just show that it somewhat emanates from the North Pole and enters back or loops back into the South Pole. Now, how do we know that this is the direction of magnetic field? This magnetic field line is actually based on experiments. Remember that we discussed the rules in drawing electric field lines. The same rule applies for magnetic fields, where no magnetic field lines should cross each other, and so on. Now, for a current carrying wire, this presents a much clearer picture of magnetic field lines, because when you have a current carrying wire and the current moves this way, then using right hand rule, the magnetic field just circles around the wire. Using the right hand rule, if I point my thumb in the direction of the current, then the direction of my fingers when I curl it around this wire is the direction of the magnetic field. So again, you just need to use the right hand rule to determine the direction of magnetic field. Again, when using right hand rule, just point your thumb into the direction of the current and try to curl your fingers. The direction of your fingers dictates the direction of the magnetic field. Let's try to visualize the magnetic field on a current carrying wire by imagining that it penetrates a plane that is parallel to the current carrying wire. So before that, let's review some notations of visualizing vectors. For example, I have a magnetic field vector represented by vector B, and it is equal to 5 Tesla. So I can represent this vector as an arrow. This is a typical drawing of an arrow. Now, if I look at the arrow when the arrow is pointing away from me, then what I can see is the crosshairs of the feather. When the directions of the vectors are represented by this symbol, then we call the direction of such vectors as into the page. On the other hand, when I look at the vector in this manner, then what I can see is the tip of the arrow. And when I represent vectors or magnetic field vectors this way, a bunch of circles with dot in the middle, then it is understood that the vector is pointing out of the page. So let's now try to visualize the magnetic field through this current carrying wire by placing an imaginary plane containing this long wire. I created a separate video for applying the first right hand rule and the second right hand rule in electromagnetism. Please watch this video. The link of the video is in the description box below. So if I try to draw the magnetic field lines on a plane containing this current carrying wire, it looks like this. So next, what if we have a current carrying loop? So the current enters this part of the wire and then moves this way. So if I try to draw the magnetic field lines, I'll just use this setup, but since it circles around, it looks like this. Let's now draw the magnetic field lines of a current carrying coil or solenoid. So if you have a very long coil or solenoid, the magnetic field lines inside it are almost parallel lines. And then loops back into the coil. Since magnetic field lines do not originate and terminate at a particular point in space, they are continuous loops. Magnetic field lines are actually continuous loops. And this figure, some of the magnetic field lines somewhat originate from infinity, but actually they are actually looping back from this set of magnetic field line on the other side of the coil. So recall our definition for flux. So a flux, in our class, we symbolize flux or we represent flux with Greek letter phi, and it is equal to the integral of dot product of the vectors to an area. So for the magnetic flux, we put a subscript m for magnetic flux, and it is equal to the dot product of magnetic field vectors and the area. So if we calculate the magnetic flux through a closed surface, we put a circle on this integral sign to denote a closed surface, and this is our equation for magnetic flux. So the SI unit of magnetic flux is Weber. So 1 Weber based on this equation is actually equal to 1 Tesla times meter squared. So let's try to go back to one of these sources of magnetic field. Whatever setup or whatever system I choose, so for example, I choose this permanent magnet. If I try to enclose this with imaginary Gaussian surface like this, notice that if some of the magnetic field lines passes through this imaginary Gaussian surface, note that these same magnetic field lines will enter again this Gaussian surface. Remember that I emphasized that magnetic field line loops back to itself, okay, something like that. The magnetic field lines emanating and passing through the Gaussian surface actually returns to the same Gaussian surface. In other words, the net magnetic flux is actually zero for a closed surface. And this is true for all sources of magnetic fields. Therefore, the magnetic flux through any closed surface is always equal to zero. This expression is also known as Gauss' law for magnetic field. As a consequence of this expression, if we have an object and this object produces magnetic field or radiates magnetic field, and this magnetic field do not terminate on another object just like an electric field, and if I try to enclose this with an imaginary Gaussian surface, then by Gauss' law, this must not be equal to zero because all the magnetic field lines passes through the Gaussian surface radially outwards. But because of this expression that the magnetic flux through any closed surface is always zero, this goes to show that magnetic monopoles do not exist or are not yet discovered. Let's now discuss the magnetic force experienced by a wire due to a magnetic field. So consider this long wire where the current flows this way, and let's just try to draw an imaginary coordinate system. So this is the x-axis, the y-axis, and the z-axis. So imagine this wire is submerged or is in an area where there is a uniform magnetic field. This magnetic field is along the y direction. Now, to examine the overall effects of this magnetic field through this wire, let's first zoom in, or let's consider first an infinitesimal element of this wire. Let's try to consider this infinitesimal element, and let's zoom it here. Imagine this is the wire, the portion of the wire, and let's denote its length as dl. So this length represents this infinitesimal portion of wire, and its direction is this way. That's why it's in vector form, and the magnetic field points this way. So I made a separate video discussing the first right-hand rule and the second right-hand rule used in electromagnetism. Please watch this video. The link of this video is in the description box below. So using the right-hand rule, the resulting magnetic force points this way. We already derived the expression for the magnetic force experienced by a charge Q that has a velocity vector of v, and it is submerged in a magnetic field B. Now, if I'm considering the magnetic force for an infinitesimal length of wire, by the way, this wire contains moving charges in this direction, and this amount of charge, let's represent the amount of charge contained in this infinitesimal length of wire as dq. So we could actually convert this equation in terms of the infinitesimal magnetic force experienced by this bunch of charges. So I'll just turn this into dq. And since we're considering an infinitesimal amount of charge, we could represent them with a singular velocity vector as if all of those charges have the same velocity vector. And we cross this with the magnetic field vector B. So let me rewrite this equation. dF equals dq. Remember that the definition of velocity is displacement over time. So in this setup, a charge is displaced by a length of dl in this infinitesimal length. So we replace this variable here with the definition of velocity, which is displacement over time. Now if I try to transfer this dt to dq, then I now have an expression for the magnetic force in terms of current. We already learned that a current carrying wire is set into motion when it is submerged in a magnetic field. When this current carrying wire is formed into a loop, one of its common application is in DC motors. The figure shows a rectangular loop of wire being sandwiched by a portion of magnet. So to understand the magnetic force and torque on a current loop, consider this setup. This yellow conductor here is our rectangular loop of wire, and it is being sandwiched by these two blocks. These two blocks is actually a portion of a magnet, so you can visualize this as a portion of a U-shaped magnet like this. This red block here is the north pole of this magnet, and this blue block here is the south pole of this magnet. So if these two blocks are magnets, you can visualize magnetic field lines coming from this red block towards this blue block. So let's assume that this magnetic field is uniform. So just imagine there is magnetic field emanating from the red block towards the blue block. So when this rectangular loop conductor is at this position, these tips are in contact with these gray conductors. So these gray conductors are obviously connected to this green block. So this green block can be a sophisticated circuit, but for our purposes, this green block just provides an EMF source for the entire circuit. At this position, pushes the positive charge on this terminal. So effectively, there is a current flowing in this path. And since this yellow conductor is in contact with this gray one, then there is a current flowing through this path and circling around the loop, and effectively, current flows through this entire circuit. So let's assume that the length of this rectangular loop here is A. The width on this side is represented by B. So let's try to denote a quantity that represents the area vector of this rectangular loop of wire. So if I multiply A and B, then I'll be able to obtain the area of this rectangular loop of wire. Apparently, this area vector has a direction normal to the area. So this is the direction of area vector. I'll represent it with vector A. Vector area A is at 90 degrees with the magnetic field vector. So let's try to observe the magnetic force experienced by the rectangular loop. The current flows this way. So using the right-hand rule, it experiences a magnetic force that goes this way. So the magnitude of this magnetic force is equal to the current times dl, or the length of this portion of the loop, which is A, then cross product with the magnetic field. So currently, this portion is at 90 degrees, so sine 90 equals 1. So apparently, there's supposed to be sine theta here. The current is at 90 degrees with respect to the magnetic field vector. So this is actually sine 90 degrees. Let's focus on this portion of the rectangular loop with width B. Now, since the current at this portion and the magnetic field lines are anti-parallel with each other, then their angle between each other is 180 degrees. Therefore, if I try to write down the magnetic force on this side, then it will be 0. We won't write it here. The current on this side flows in this direction. And using the right hand rule, the magnetic force it experiences is along this way. So if I try to write the magnitude of the magnetic force, then it looks like this I, A, B. Then again, at this portion, it's sine 90 degrees. But I won't write it here since it's equal to 1. But its direction is opposite to the direction of this side. So there must be a negative sign here. So it turns out that the summation of translational magnetic force on this rectangular loop is 0 because they are in opposite direction but same in magnitude. However, if we try to focus on the torque that this rectangular loop experiences, so I'll just calculate first the torque on this side. So it's equal to R cross F. R cross F. So for the magnitude of the torque, our R here is obviously B over 2. Then F is IAB. So I'll try to write down sine theta here. Though I know that theta equals 90 degrees, I'll still write it here anyway. And the torque here, the magnitude of the torque here is also B over 2 IAB sine theta. Now since these two values of torques rotates the system in a counterclockwise manner, they have equal sign. So the total torque is equal to BIAB sine theta. Or I can regroup the variables. T equals IBAB, which is area, sine theta. Let's try to represent the factor current times the area with the variable mu. And torque becomes mu b sine theta. Based on the second right hand rule, if you have a loop that looks like this and the current flows this way, then it will produce a magnetic field that looks like this. Now if we assume that mu is a vector, then we could represent its direction the same as the direction of the area vector. However, we designate the positive direction of mu in such a way it coincides to the magnetic field produced by the current carrying loop. So in a way, if we have this kind of rectangular loop and its current flows this way, then the direction of mu is this way, the positive mu. And since we already converted mu into vector, then this torque above can be rewritten as mu cross B. So in this figure, the direction of mu is along this way, and the direction of magnetic field vector is along this way. So the angle between them is represented by theta, and it is the same theta we have been dealing with. This mu with the magnitude of current times area shows up many times in calculations involving magnetic fields, and they gave this a special name, and this is actually called magnetic dipole moment. Again, we already derived the vector torque on a current loop. So this expression tells us that if you have a loop, conducting loop, and current flows through this way, then we can represent it with a vector called magnetic dipole moment, mu. And its direction is the same as the direction of the magnetic field produced by this current carrying loop. So when it is submerged in a magnetic field, This current loop experiences a magnetic torque, and this torque tends to align mu with the direction of B. So when a current loop experiences a magnetic torque due to the presence of external magnetic field, then we call this current loop as a magnetic dipole. So recall that in electric field, we have the expression torque equals P cross E, and it is a similar form with this one for the magnetic field. Now also in electric field, we have the expression for the potential energy, negative P dotted to E, where P is the electric dipole moment. Similarly, we can derive an expression for potential energy for a magnetic dipole. And copying this form, we have U equals negative. Since we replace electric dipole moment with magnetic dipole moment, this is equal to mu dotted to, instead of electric field, we have magnetic field. So this is our expression for potential energy for a magnetic dipole. We are now familiar with the magnetic force experienced by a rectangular conducting loop, and we apply this principle to PMMC, or permanent magnet moving coil. So imagine I have the same magnet here, the north pole of a magnet and the south pole of a magnet. In the middle of this magnet, there is a cylindrical object, and in this cylindrical object, there are many coil of wire. So in effect, one turn of the wire is equivalent to this setup. So there are many coils of wire wrapping around this cylindrical object, and we attach a needle on this cylindrical object. Now this cylindrical object is free to move or deflect or rotate with respect to the magnetic field. Above this needle is a scale that is calibrated, and it has a label of 0 here, or 5 here, and then 10 here, and so on. So when current passes through these coils, obviously this will result to a rotation of the cylindrical object, and this will result to a deflection of our needle. But instead of continuously turning this cylindrical object, it is connected to a spring that somewhat counters this deflection. A permanent magnet moving coil, or PMMC, which is also known as Galvanometer or galvanometer, is an instrument used for measuring DC signals. So in this setup, this conducting coils is actually connected to a wire, and this wire supplies the current that flows through that coils. So PMMC has coils of wires suspended in the field of a permanent magnet. The deflection of its needle is primarily caused by magnetic force. When current flows through the lightweight coils, these coils experiences a magnetic force. The meter deflection is proportional to the current supplied in the coil. This rotating part of the instrument is attached to a spring that exerts a restoring torque. The restoring torque is proportional to the angular displacement of the needle. And the scale here is calibrated in such a way there is a proper translation between current reading and the angular displacement of the needle. So that's the basic operation of PMMC. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!